Thank you all for coming here today. My name is Kate, and I'm going to be concluding panel 5, The Future is Now, by talking to you guys a little bit more about the capture, conversion, and utilization of abundant CO2 for energy production for research on Mars. I'll start by telling you a little bit about why traveling to Mars is important, how CO2 plays a part in that, and introduce you the model that I constructed that will connect all these things. Next, I'll talk about the methods in which CO2 can be used and why it's important that we compare and combine these methods to each other and to new ideas. And last, I will conclude my investigations by proposing what else I think we could do with CO2 and the impact that all of this will have on technological innovation. Mankind has always had its eyes set on the stars. But until the 20th century, we were unable to reach them, let alone surpass them. Since manned spaceflight started in 1961 with Soviet cosmonaut Yuri Gagarin, we've achieved many great feats. Hundreds of probes have been set throughout the solar system to better characterize it, and hundreds of astronauts and cosmonauts have taken flight, 12 of which have walked on the surface of the moon. With technological advancement and the will to progress, our sights are now set on sending humans to Mars. NASA has already sent dozens of probes and rovers to better characterize its chemical composition, its atmosphere, and its geological features. This begs the question, if these probes and rovers are already collecting this data, why do we need to send humans to do that? It's estimated that having human researchers on Mars could lead to discoveries being made approximately 10,000 times faster than even the most technologically advanced robotics. So even with more competitive probes and rovers, sending humans still has other benefits. This endeavor would also support commercial and industrial growth, scientific and technological innovation, and our understanding of Earth. So therefore, there is consensus that sending humans to Mars would have benefits that will positively affect society and call for additional research and testing of our current technology. What's the problem? When sending anything into low Earth orbit, there's going to be a high payload cost associated with that. The cost for sending just a kilogram of materials to Mars can range anywhere between $1,700 to $20,000. And that depends on the company and on the rocket. In addition, there's going to be a need for life support. Our human researchers are going to want breathable oxygen, drinkable water, and then durable and energy efficient habitats. If we were to bring all these things to Mars from Earth, our payload cost would literally skyrocket. This is why it's necessary to look to naturally abundant resources that could be utilized for energy and to sustain human life on Mars. One of these primary resources being investigated is CO2. So what is CO2 and why is it so important for sending humans to Mars? CO2, the big discussions about it are mostly pertaining to climate change and global warming, which is real, and how it's impacting the human health and human life. CO2 is a colorless trace gas that is naturally found in the Earth's atmosphere at a concentration of approximately 0.04% by volume. Unlike Earth, Mars has an atmospheric CO2 concentration of about 95.5% by volume, as measured by NASA's Curiosity rover. So when planning any type of manned mission, it's important that we look at the time frame, the duration and the size, the steps, and the energy required for these missions. The following model that I've created it will encapsulate these elements so I could better have an idea of how much CO2 will be needed and when it will be needed. So I could better analyze the efficiencies of these methods and which ones should be implemented in future missions. The following model encapsulates these elements so that, looking at low Earth orbit missions and then current and ongoing missions and projects that are being planned by like NASA's Journey to Mars, SpaceX's Falcon Heavy, and NASA's Design Reference Architecture 5.0. I was able to take into account their decisions for their models and then implement them and modify them into my own framework so I could better make these comparisons. So for Mars specifically, we know that the synodic period, the time when Mars will be at the same and closest orientation relative to Earth, is about 26 months. Therefore, every 26 months, there's a window in which sending payloads or missions would be more cost and time effective. These missions would be approximately would have a 9-month travel time from Mars to Earth or Earth to Mars. Higher energy and faster flight times are possible, but they are not cost effective and thus will not be considered in this research. And following NASA's In Situ Research Utilization, or ISRU, we're going to use a crew of 6 for this research mission, and they're going to be on the surface of Mars for 18 months in this model. The previously mentioned projects consider anywhere between 3 to 7 pre-deployment missions, and their overall projects are typically broken down into 2 to 3 stages. So like NASA's Journey to Mars and NASA's ISRU systems, I'm going to just stick to 3 stages. Stage 1 starts with the Earth-reliant investigations and ends approximately in 2024. It'll start with the testing and research for power, mining, and life support, and end with the installation and construction of an efficient propellant plant on the Martian surface. The 2 phases outlined in orange here are the actual missions that are being planned by SpaceX. Stage 2, from about 2024 to 2030, will consist of the proving grounds and research acquisition, where testing and validation of deep space habitation will be completed before we send any humans into Martian orbit or to the Martian surface. Pre-deployment will be done during these low energy windows during the synodic periods to bring the necessary cargo and ISRU units to start producing this oxygen for fuel and for air. Stage 3 is the beginning of the manned missions, orbiting and eventually landing on Mars. It's expected that we'll have our first humans set foot on the planet by 2033. The missions outlined in red here are the focus of the CO2 extraction and conversion techniques in this research. We want to know which methods are the most efficient in the terms of the amount of product produced in about 300 days for these potential pre-deployment missions. Ideally, these missions would be set about 2 years before sending any manned missions, as to allow for time for the cargo to get to Mars and to allow for time for the fuel and the air to stockpile so that we can send our researchers and their researchers back to Earth. And this is all based off the ISRU design. So how do we use the CO2, and then how do we capture and or convert it? Simply put, carbon dioxide can be converted into liquid oxygen, which can be used in conjunction with methane to produce rocket fuels. In addition, CO2 can be converted into breathable oxygen and drinkable water, life's favorite solvent. In addition, some of these resources will be necessary for some of the research projects that these explorers will be conducting while on the Martian surface. Method 1 is going to be covering oxygen production. Method 2 is going to be covering methane and water production. And method 3 is actually a capture method for the CO2. So before we start, here's a little bit more on ISRU. Because the Martian atmosphere provides an essential exploration site resource, CO2, a proper ISRU system and system architecture can be employed to significantly reduce the launch weight, size, and cost. This is important because explorers will have less access to life-sustaining elements and resources that could be easily acquired back here on Earth. This system, developed by NASA, involves concepts for extracting and utilizing natural resources from the Martian atmosphere or even from the soil. But like this project, it also focuses on utilizing CO2, hydrogen, and methane. The main methods in this ISRU that need development are the atmospheric CO2 collection, the methane fuel production, and the water electrolysis subsystems, all of which use methods 1 through 3. The first method being solid oxide electrolysis, or SOX. Innovators at NASA's Glenn Research Center have developed a method for producing pure high-pressure oxygen via an electrochemical pumping process through a solid electrolysis cell stack. This works by applying a voltage across an oxygen ion conducting ceramic membrane to generate pressurized oxygen by electrochemically splitting the CO2 at the cathode, the positive end, and then converting it into O2 at the anode, the negative end. This oxygen can then be pressurized and stored for later use. SOx is already being implemented and researched as part of phase 1 in our model through NASA's Mars 2020 mission. The 2020 mission has all types of experiments to answer key questions about the potential for life on Mars and also for searching for past signs of microbial life. To help prepare for human exploration of Mars, one experiment in particular, MOXIE, is going to help us a lot. MOXIE will demonstrate the SOx IRCU method by producing oxygen from the Martian atmosphere. It produces about 10 grams of oxygen per hour, or about 240 grams per day. Because this method is only going to be analyzing the purity of the oxygen, it's not going to be storing any of it. So this mission is acting as only a proof of concept for stage 1 in our model. Our second method is the Sabatier reaction. Originally developed by Nobel Prize-winning French chemist Paul Sabatier back in the 1900s, this process utilizes a catalyst that reacts with carbon dioxide and hydrogen, both of which are byproducts of the current life support systems aboard the International Space Station to produce methane and water. The basic system design typically consists of 4 main unit operations. The first being a regenerable CO2 adsorber to separate carbon dioxide from other atmospheric compounds, such as argon or nitrogen. 2, a CO2 accumulator and compressor that will store and manage the CO2 flow to the Sabatier reactor. 3, a methanation reactor that reacts the CO2 with hydrogen to produce the methane and water. And 4, a solar-powered water electrolyzer that produces the oxygen and then recycles the hydrogen for future use. This method produces, on average, 340 grams of water per hour. And the third and last method that I'll be discussing today are zeolites. Zeolites are microporous aluminosilicate minerals that are commonly used as commercial adsorbents and catalysts. First, it's important to distinguish the difference between absorption and adsorption. Absorption, the process that you're probably more familiar with, is a process in which a fluid is dissolved by a liquid or a solid absorbent, like a paper towel. Adsorption, on the other hand, is the process where atoms, ions, and molecules adhere to the surface of an adsorbent, like a zeolite. As mission durations increase and the exploration goals reach beyond low Earth orbit, the need for in situ regenerable adsorption processes for continuous removal of CO2 and other chemical contaminants from cabin air becomes really important. When exposed to air, CO2 simply adheres to the zeolite and can be removed or regenerated by simply heating it, thus filtering the air and acting as an oxygen concentrator. In fact, this technology is commonly used in medical equipment such as CPAP machines to filter the air. The implementation of zeolites for the absorption process is of interest due to their ability to selectively remove contaminants and because of their chemical inertness and non-flammable properties. It is important that this is important because flammable materials are not welcome on our spacecraft due to safety and health concerns. Finally, to achieve optimal usage of these well-developed methods, they need to be compared and combined to one another or to new ideas. One tested example of the combination of scientific methods has been conducted by NASA-supported research at Precision Combustion Incorporated. They've demonstrated that zeolites coated on their patented microlith mesh material can effectively absorb a number of contaminants of interest, such as CO2, ammonia, and ethanol. Furthermore, these sorbent materials can be readily regenerated, meaning they don't need to be replaced, and they can be smaller and lighter than the current adsorber beds that are currently being used. In addition, they can be directly applied to our Sabatier reactions with high efficiency. Current applications of zeolites can continuously remove approximately 5,700 grams of CO2 per day. Therefore, from this research, it was determined that these zeolite materials, when combined with the Sabatier reaction, are suitable for the removal of CO2 and could potentially be applied to these future Mars missions. For the remainder of my project, I have been working on determining the best landing and habitation sites for some of these future missions for Stage 2 and Stage 3 of this project's model. Part of this is I want to propose a method for CO2 extraction from CO2 ice that forms during the poles during the Martian winters. I believe that this could supplement or act as a replacement for atmospheric extraction methods or even use these methods. So having a research site that is well characterized and far enough away from the Martian poles to not freeze over would be ideal. Since we need abundant CO2 to perform CO2 ice to perform a CO2 ice extraction, we need to take a look at where previous missions have landed and characterized, relative to where the ice would be forming during a Martian winter. Up here in blue is the polar zone, which is covered by CO2 frost during the Martian winters that sublimates away during the summer. And down here in green are the transitional and temperate zones. They will also be very cold, but they won't be frozen over, so this would be an ideal place to have a research and habitation site. Oh, my bad. A previous mission that has characterized land in the polar zone is the Phoenix mission, in Fastidius Borealis. However, a research site in this area would not be ideal because it can be covered in as much as 3 feet of CO2 ice due to the polar ice cap. On the other hand, although Viking 1 and Pathfinder have both worked on characterizing Cryosplanitia, this location is outside of the temperate zone, and so if researchers decided to use this as a place for a future habitation and research site, they would have to move approximately 2,000 kilometers just to reach the edge of the polar zone, and this is way too far. So, since that's too far, we could use a site that's perhaps north of the Viking 2 landing site in Utopia Planitia, since it's been well characterized and it's within the transitional temperate zone and closer to the polar zone. When CO2 ice is heated, unlike water, it tends to skip the liquid phase and go straight to the gas phase. Therefore, CO2 ice could be compatible with the SOx or Sabatier reactions when they're paired with zeolites to produce oxygen, methane, and water. I'd like to investigate other conversion methods, but it's also important to note that CO2 ice, when put under certain pressure and temperature conditions, can be converted into the liquid phase. And liquid CO2 is a very useful organic solvent that could potentially be used in some of these research projects that will be conducted on the Martian surface. So due to the naturally high abundance of CO2 in its atmosphere, finding new ways to use it could therefore lower costs for future in situ Mars missions that would require samples to be returned to Earth. Additionally, investigations for finding other useful natural resources for long-term habitation is already underway. And to conclude, it's important to remember that what overall effect that all this research will have on the technological innovation here on Earth. Like the space race in the 50s and the 60s, I believe that the impact of CO2 utilization research will promote technology that will benefit future generations and perhaps even save the planet that we currently inhabit. Thank you.